In this video, we are going to demonstrate the tool Immersive Software Archaeology, or short, ISAR. The idea of ISAR is to ease the process of comprehending unfamiliar large-scale software systems by first automatically analyzing their source code and, based on that, visualizing them in form of real-world 3D structures, namely a solar system with planets, cities, and buildings that users can then explore in immersive virtual reality. Automated analysis in Eclipse. Users start the exploration process from within the Eclipse IDE, where ISAR provides a platform of extensible Eclipse plugins that allow users to fully automatically analyze a system structure from architecture level down to source code level. Because the organization of a system in folders, packages, namespaces, or similar structures does oftentimes not represent a logical decomposition in cohesive architectural components, ISAR's analysis encompasses a fully automated software architecture recovery method. All that it takes to analyze a system and thus create such a model is to select one or more Eclipse projects, depending on how users define the system, and hitting this button. A dialog opens that lets users choose between a variety of options for different steps of the analysis. These correspond to plugin extensions for ISAR's extensible analysis platform. As part of ISAR, we include an analysis for Java systems. However, developers can implement own analysis plugins for other languages as they wish. Further settings for the different plugins can be found in the menu here. Immersive exploration in virtual reality. After having analyzed the system, users can explore and thereby comprehend its architecture and design in virtual reality. After launching the VR application, users select the system they wish to explore, and after it is loaded up, immediately start their journey. To facilitate users' ability to solve software comprehension tasks, ISAR's virtual reality visualization offers three key features. Architecture overview. Initially, ISAR provides users with a room-scale overview of a system's architecture, where high-level architectural components are represented as planets. Planets contain hierarchies of land pieces, similar to how land is hierarchically organized in the real world, with continents, countries, regions, and so on. On the lowest abstraction level, architectural components are represented as cities, with classes as their buildings. Users can interact with the architectural elements. They can open meta information on planets, continents, and cities, where they can inspect a summary of often used words to gain an impression of the content, or inspect metrics such as the number of contained buildings. Semantic Zoom. To avoid overwhelming users with details, the smallest visible entity in the architectural overview are buildings, which represent class-level elements. Users can semantically zoom in on a city by navigating to it. This locates them on the surface of a planet, just changing their perspective from an architectural overview to a first-person design-level exploration. In this semantically zoomed-in view, buildings are represented in more detail. They consist of individual floors, which each represent a method or constructor. The shape of floors is determined by metrics about the respective method or constructor, where complexity is the diameter and number of expressions is their height. Furthermore, their accessibility is encoded via visual decorations. Public methods have large windows, private and protected methods don't. Abstract methods and interface methods are represented as hollow construction sites, indicating their unspecified character. This allows users to gain a visual overview of an entire class without reading through its code. However, users can very well read the source code of a class by opening meta information on its representing building. Interactable relationship graphs. To help users with relating elements to one another, for instance, to identify cohesive units of classes, ISAR embeds interactable relationship graphs into all levels of its semantic zoom. By using these, users can inspect references between software elements based on method calls, field accesses, and type references such as inheritance. For instance, they can inspect all outgoing references of a building. Users can extend the relationship graphs to find transitive relationships in a system. The same principle applies for incoming references. With the same technique, users can display relationships between architectural components, in this case a planet. To display relationships of architectural components, ISAR agglomerates lower-level relationships to the respective level and bundles their edges accordingly. The level to which ISAR agglomerates and bundles relationships can be configured by the user. With these features, our tool Immersive Software Archaeology aims at facilitating software archaeologists with recovering knowledge on unfamiliar large-scale software systems, with their code as the only source of information.